Welcome to week 9 of our Onshape videos here. Um, we only have one more week after this, and then the CAD class is all done. So I realized that I made a slight error when I was talking about what the upcoming schedule was in our video last week. Um, I had said that we were going to be doing a 2-week project this weekend next. However, I mixed up what the plan was for these videos. So this week we're going to be kind of going back to a little bit of a format that we were working with early in the CAD class, where we were kind of not working on a project. We were just kind of demonstrating some features. And then next week there's going to be one final project for the CAD class. We're going to kind of just power through it and do it all in 1 week next week. Because we've already been through a few of the projects, so I won't quite explain everything in as much detail next week. We'll kind of just go through the motions of what we've already learned. There will be a couple of new concepts that we'll go over, but we'll save that for next week. So what we're going to be talking about this week is drawings. Basically, a drawing is kind of a 2D plan view that we can print out on a piece of paper or save as a PDF that can be viewed by basically anyone without needing access to a computer in the case of the printed version, or without needing access to the CAD software in the case of like a PDF or similar file format. Drawings are a very, very important part of engineering and CAD and design in general, because generally out in kind of the real world, nothing gets manufactured without a drawing. That's really pretty true across the board. That's becoming less and less true over time as CNC equipment becomes cheaper and more ubiquitous, and 3D printing and additive manufacturing become more common. That's causing some of the reliance on these kind of 2D drawings to go away. However, that process happens very, very slowly, and more traditional manufacturing styles still kind of rely on drawings as the primary method of exchanging kind of design information. So I'll go into that a little bit more here in a second once we kind of have something to look at, and it'll make it a little bit more clear what I'm talking about. So what we're going to do first, I'm just going to work in this project that we worked on from last week and the week before. We're going to just make some drawings for some parts that we designed here. I figure this will be a pretty good demonstration. There's no real need to model new parts for what we're doing here. So just to kind of keep things organized, I'm going to create a new folder called drawings. I like to keep drawings kind of out of the way of all of the actual modeling stuff. So one thing to understand here as we're creating a drawing is that I mentioned how important drawings were for kind of out in the real world, like a job you might have in the future. Drawings are going to be a very big part of any engineering job. However, in the context of FRC and specifically the RoboChargers, drawings are actually not a very big part of what we spend our time doing in terms of design. Basically, many of you guys that were on the team, over the past seasons, will know that anytime we 3D print a part, you just pull that STL out of the CAD file and you just go and 3D print it. Anytime we cut a flat part on the router, right, like a bracket or something out of polycarb or aluminum, we just export a DXF and we just take it over to the router and we plug it into the CAM software and we cut the part. There's no drawing, there's no paper, there's no PDF, there's nothing like that. The only parts that really get drawings are parts that are being manually machined with the mill or the lathe. So shafts or tubes that get weird hole patterns drilled in them or stuff like that. So basically, there are only going to be a few drawings that need to get made every year. However, it's very important to know how to do it ahead of time, just because when we're in the time crunch and we're getting the robot, we're getting parts rolling out for getting the robot made, you know, being able to just whip up a quick drawing so you can run over the mill and make a part or whatever is an important thing to be able to do kind of on the fly, I guess. And then obviously, as I mentioned, the drawings will have a larger importance to you in a future career and future engineering job. And so it's important to kind of get used to how to work with them as early as possible. So we've created this drawings folder. I've clicked on it to go into it, and then now we are going to just add a drawing. Pretty straightforward. There's a bunch of templates. You can create these yourself, but I have not bothered to create one for RoboChargers yet. I will probably get around to doing that at some point, or if someone on the team wants to do it instead of me, I would love to hand that off to someone else. Um, so there are some different sizes. A, B, and C are the common sizes, but there's different sizes as well. ANSI A is basically 8.5 by 11. That's just like a normal piece of printer paper. And we're going to do everything in inches, so this default template's already selected here is the one we're going to want to use. So we could just click OK. All right, so we get basically a sheet of paper that already has some stuff on it, and then we get a dialog that pops up automatically that wants us to place a view. So we basically got to just decide which part that we want to create this drawing for. So I'm going to just go into components and just kind of look through here. And I'm going to pick, I'm going to pick this bracket here, which is the like main pivot bracket, I believe. Now we kind of get this, this box, and then eventually it'll load a preview. And what it's asking us to do here, I'm not clicking or dragging, I'm just moving my mouse around and this thing's just following me around. Basically what we're doing is we're placing a view of the part. Now what we're looking at right now is an end view. And so obviously because it's a thin plate, it's, you know, kind of just this straight line that we're looking at. But if we want to look at like the right view, now you can see, you know, the part has kind of, you know, more shape. And it's basically just a line drawing. There's no shading, there's no coloring, it's just lines. You can change it to show shading, I believe, but you generally don't want to do that for, you know, drawings, just because looking at the lines is a little bit more clear what arrows and things you're pointing to. And then also when we're printing these on the printer, right, you don't want to use a ton of ink by having a shaded colored view of the part. So I'm going to click just to kind of place this down. Now it keeps up this this kind of like little display going, where if I'm moving my mouse around, it's showing, you know, different orientations of the part. What I placed here is often called a base view, and then what it's trying to do off to the side here is place what's called a projected view. So basically, like, we're looking kind of a front view of the part, and then like I can place a side view over here, or I can place a different side view over here. You'll notice these are slightly different between this one and the one over here. Basically, you know, I'm looking at, you know, the front or the back or the top or the bottom, and so if I click, I place that view down as well, and I can continue to do that and place more projected views if I want, but I'm just going to escape out of this tool for now. Okay, so there's a few things here. If I move this around, you know, this will always stay aligned to it. These need to stay aligned to each other. There's ways to break this alignment if there's some reason why you need to do that. However, that's not really something you need to do very often. So basically, we can, if you want to ever go back and add more projected views, you can go up to the top here and click projected view. This here is the base view, by the way, just the base one that we started with. If you hit projected view, you select the view, then I can place like a top view. But I don't actually want that, so I'm going to hit Control Z to undo. There's a few other types of views that we can create that might be useful. So there's a detail view that's pretty common. It's like a little pop-out bubble, basically. So if there's some part of the part that I need to get a closer look at for the purposes of the drawing, I can click on detailed view. I can, I don't know, select some area, I basically select the center point where I'm creating a circle. I'm going to move my mouse until the circle is the right size, and then click again. And then basically it'll create, this kind of little pop-out bubble that shows, that detail in, kind of a larger size. And I can like this A little label here. So this says detail A, and this little marker here has the A on it. So that's how you know the two views go with each other. I can click and drag on this to relocate it or resize it, get the A kind of out in a more visible space, and then this view will update as I change this here. I can move this around a little bit, and the view should update. Oh, it snapped back to where it was. I think I'm attached to geometry here. Anyways, you'll only use these on really, really complicated parts. However, these are pretty useful. I'm going to go ahead and delete this because we don't need it. There's also a section view. A section view doesn't have like a ton of utility for a part like this, but if there's some part where I need to show a more detailed view of a cross section, or if I'm doing a drawing for a complicated assembly, maybe I want a section view that kind of cuts the part in half and looks at, the end of one of the sections. If I want to do that, that is this guy right here. So if I hit section view, I can either do vertical or horizontal or at some angle. I'm going to do vertical. I'm going to pick the center of one of these holes, and then you need to choose which side you want to have the view facing towards. I'm going to go this way. And then basically it places very similar to a projected view. Once I place this down and it shows the display, you'll see we can kind of see here where there's these holes show up because I'm cutting a cross section through the hole. And you see these hatches, these little angled lines, basically showing that this is a cut surface of the part that that we're looking at here. So this is another useful feature as well if you need to show the inside or the cross section of something that you can't just get by using an end view. Once again, for this part, this wouldn't be that useful of a view, so I'm just going to select it and hit delete. Okay, so let's continue on. Those are kind of some of the basic views that you can create. There's more things you can do. You can click break view, which makes like long parts shorter. Kind of breaks out the middle section of a long part. You can crop views. You can create cutouts. You can create more complicated detail and projected views. But we're gonna kind of stop there for now. And if you want to play around with those, you can. Okay, so let's talk about dimensions. So when you've got a drawing like this, the most important thing you're going to need to put on the drawing once you've created your views is dimensions that tell the person looking at the drawing how big all of the different features are, how how far apart they are, what the spacing is, diameters, radiuses, angles, things like that. So basically creating dimensions in a drawing like this works exactly like it does in a sketch. However, the only difference being you can't type a number into the dimension once you create the dimension like you can in a sketch. You'll just place the dimension and the number will just display whatever the number is that corresponds to that piece of geometry on the part. So you just need to place them down in a way that's very readable. Essentially, you're not doing any design work here. All you're just doing is making a document that is very readable to whoever's looking at it. So let's create some dimensions. Let's kind of talk about some useful ones here. So the dimension tool is this guy up here, or you can just hit the D key. Just like in a sketch, I can create a dimension that is just the length of a line just by clicking on the line and placing the text down. That's pretty useful. Obviously this is not super useful because this part has radiuses on the corners. So if I wanted to dimension, for instance, the entire width of the part, I would need to click two lines and place the dimension down in between. Basically, this is going to be a pretty common way you're going to do it. This works just like it does in a sketch. Then there's a few other types. So if I wanted to do an angle dimension, I can click on two lines that are not parallel and I will get, an angle. That's pretty useful. I'm going to delete this, get it out of my way. And then in addition to that, there are radius and diameter dimensions using the same tool. So if I click on, one of these holes, I get this little symbol here, which means diameter, and it tells me the diameter of the hole. I can click on one of the corner radiuses, and I get the radius of that corner. Basically, just all the same stuff that it does in a sketch. I can click on these dimensions and move them around, and the arrows will change and update. Just like you would expect. Okay, so basically that's all you really need to know about the dimension tool. We'll talk about exactly where to place dimensions here in a second. But the next thing I want to talk about is a little bit more of an advanced dimension tool that allows. It's called an Ordinate Dimension, and it allows you to basically show the X and Y positions of a large number of instances. So something that might be useful on a part like this is we've got this row of holes. When you're working on like a mill or something like that, you actually need to drill these holes usually using the X and Y coordinates of these holes based off of some, pre-specified, 0, 0 point on the part. So for example, a lot of times you'd use a corner of the part like this corner over here and drill these holes based on the X and Y coordinates based on that corner. So there's a tool up here called Ordinate Dimension that allows us to do that. We have to place the X and the Y ordinate markers separately. So we're going to start with this direction here, what I guess you could call the X, but it depends on what orientation the part's in the machine. I'm going to pick a surface here. I'm going to start with this line, I think, and just click on a point somewhere. And this basically is just specifying the 0, 0 point. So if I click on it and then I place down the 0, 0 marker, wherever I want, then basically I just need to go and click all of the center points of these circles, and it'll put these little markers that tell it what the distance is away from the 0 marker that you created. So I'm going to hit escape, and those are there. If I click and drag on them, I can move them all up and down, and I can move them individually left and right. That's all helpful if you have like a very, very tight, like cluttered part with a lot of ordinate dimensions. Ordinate dimensions can get pretty messy pretty quickly. So now I want to do this for the other direction. So I'm going to get rid of, well, it should be fine. So I click Ordinate again. I'll pick this point here, place my 0 marker down here just out of the way. And then basically all of these parts are in a line. All these holes are in a line. So I don't really need to select each one. Otherwise, it just create duplicate markers. But I don't want to select this front hole because then I don't get this line that goes all the way through them. I usually like to pick this back hole so I get this line that's showing that they're all connected on the same center line. And then I'm also going to place this hole up here. And what I'm going to do is this guy, I would actually like to connect up here instead for the same reason. So if you click and drag on these little blue dots, you can change what they're connected to. Because this hole and this hole are actually lined up, but they are, I don't want to create two separate little markers for each one. So I want this line showing that they are connected in a line. Okay, so that's an ordinate dimension. There's another important one that is there's an automatic hole callout. Now, I don't know if it's going to work on this part because I don't believe we use the hole feature here. But on a part where you use the hole feature, the hole callout tool will automatically kind of put in some important information about what the hole is. So that's especially important for like tapped holes where you have threads. This hole callout will create a note that calls out the threads and the tap drill diameter and the depth and everything that you need. So I don't think it's going to work on this part because we didn't use the hole feature. Yeah, it won't even let me select these because these weren't created with the hole feature. But this tool up here is pretty important. And this is one of the reasons why it's important to always use the hole feature if you can, because it helps you make drawings faster because you can just use the hole callout. And the hole callout will include information like quantity of holes. So like if I have all of these holes here, You know, if I were to dimension this, you know, this hole here and these holes down here are all the same size. And so instead of putting a hole call out on each hole, I would just, you know, put like a 6x note on the hole, on one hole call out, and that would be all the information that I would need. So we can just kind of do that manually by just putting a dimension here, and then we can double click on this, and basically there's this little kind of like prefix. But so basically this is the dimension. We can specify like number of digits of oops, that's not number of digits, this is number of digits, number of digits of precision. We can specify some tolerancing stuff, which we'll talk about a little bit later, and then we can also put some notes above or below, to the right or to the left, and just add text that's not related to dimension. So what we'll do over here is go over to the left text, which already has this diameter symbol in it, and then basically we're just going to do 6x space, and then we click outside of the box, and now that's added to our drawing. Things like the whole call out tool would do this automatically, but we can do it manually just like that. And if there's other notes that you would need to add to this, you know, that dialog box is a good way to get that done. So I'm going to continue kind of working here, and I'm going to kind of flesh out this drawing a little bit. So what we're going to do, I think, is, I don't know, just add a few more dimensions here. So we need a radius up here, and we need, I'm going to go ahead and add this width back in and just kind of straddle all these marks. I'm going to move this guy here, get this out a little bit, tuck that in. Okay, I'm going to do thickness here, that's important, and this angle can stay. I may change where it's positioned though. Like I said, it's very important to make this very readable, and so having a lot of lines crossing each other, or having it not be super clear where the you know, where things are connecting and what things are pointing to is pretty bad. So the only thing we got to do is figure out how to dimension this back side here. Now, like I said, I have not done a ton of drawings in Onshape. What I'm trying to get it to do is, what I would like to do is specify basically a dimension to the sharp corner of these two lines, because there's no sharp corner here, but I know that this corner here is a sharp is a 1-inch dimension, and then we added this fillet after the fact. So I want a dimension to this kind of floating point here in space that is the intersection of that line and this line down here. Now it looks like if I hit the dimension tool, snag this bottom line, and I zoom in and hover over it, it looks like it will let me do that. But I need to hover over both of these first. Oops. Oh, maybe not. Trying to get it to snap, I think. Nope, that's not gonna let me do it. Okay. I don't actually know if this is a feature in Onshape or not. I've never tried to do this before. This is a feature in most other CAD software. Onshape's SolidWorks has it, and Inventor has it, and I'm sure other CAD software has it as well. But Onshape's drawing environment is still not exactly feature complete, in my opinion. There's still some stuff that's not in the software that needs to be there before you can really create you know, all of the you know, kind of views that you want to create. So let's try to add some construction geometry to accomplish what we're doing here. So what's this? Virtual sharp, that's what we want. Okay, so it looks like if we just select these two lines, it'll just add a point for us. Okay, so then once we have a point there, then we can just dimension it to the point, and that accomplishes what we need to do. So there is a way to do it. You just got to add that point in there manually first. So like I said, I've never actually done that before, so you learned something new. All right, so then that tells us that this is,
1 inch high, because the way that you would typically make this part, if you weren't doing this in the CNC router, right? If you did this in the CNC router, you just throw the file in and it would just cut the profile and you wouldn't need a drawing at all. Um, um, but basically, if you were making this on like a mill or something manually, you would make all of these corners sharp. And so you could manufacture it using this 1 inch dimension, and then you would come in and you would add these radiuses after the fact, possibly just with a sander or some sort of deburring tool or a file or something. You wouldn't necessarily machine these rounded corners in, because there's no real easy way to do that, on like a manual mill or something. Basically up here, we don't need any kind of similar dimension on this side, because the implication from the drawing view is that this radius is a co-radial, or concentric, I guess, actually, with this hole here. Now, this is something that's important when you're creating drawings. Obviously, a drawing is supposed to be human readable, and so if you're creating a drawing and there's any weird things going on where the geometry is not what it looks like, you need to be very careful to call things out in a very clear way, because if you don't call them out, somebody will make assumptions about what the drawing is saying, and you need to be very clear. So, for example, if let's say that this radius here was not supposed to be concentric with this hole, but let's say they were very close. Like, so it looks like it's concentric, but it's not actually concentric. It would be very important to probably create a detail view of this little area, pop it out, zoom it in real big, show where the center point of this arc is, show where the center point of the hole is, dimension them relative to each other or something. You can also, if you've got really obvious stuff, you can also add text notes. Like, we can put a note on the page and we can have an arrow pointing. If I want an arrow, I just click on the thing I want the arrow pointing to, and then I click again out here, and then I just start typing. I can just do something like this. Like, I can put a note here saying that this arc is concentric with the hole. Now, normally you wouldn't need to put a note like this, because, and most people reading this drawing would just assume that this curve is concentric with the hole, because we haven't said otherwise, and visually it looks like it is. So that would be a safe assumption when reading this drawing in most cases. However, calling it out is not a bad thing. So basically, the only thing left to do is, if we wanted to, we could call out these radiuses. And this radius and these bottom two radiuses are the same. I just know that because I remember when we modeled it, we just did a fillet all. I'm going to double click on this and do a 3x just to let people know that all the radiuses are the same, except for this one up here, which we've called out separately. Okay, so basically that concludes this drawing. Now, let's talk about the rest of this page a little bit real quick. So there, this area here in the middle is kind of just our workspace, but there's also this kind of table down here below. Now, this guy is what's called a title block. This is a very common drawing feature. That pretty much every drawing from any company, from any CAD software, anywhere, will have something that looks like this. And basically the purpose of a title block is to kind of, display some overall information about what the drawing is saying. So, things like part number and material, and, who drew it and what the date was, and all of that stuff. So, we can kind of look here, and we've kind of got some of these like gray fields, and if we were to click on them, we can edit the text. So let's change. This was part. Let's go back here. This was part 4 that we were working on. Yeah, week 7_004. So let's put in our drawing number here. If I double click, I can do week 7_004. Right, that's the part number, right? That's the drawing number. If you have some different drawing number, different than the part number, you can put something else here. But here we'll just put, pivot plate, maybe give it some name, some title. I'm just gonna delete these. I don't few other things here. So some of this stuff is, you know, more useful to, um, you know, maybe businesses or more, you know, kind of professional manufacturing like environments rather than our FRC team. So over here, you know, you have this. This is for revision, right? So like, what is the version of this part? Typically, it's a letter. It starts at A, B, C, D, right? Revision is a pretty common thing for companies to track for on drawings. We don't really do stuff like that on the RoboChargers usually, although sometimes we will try to do a little bit of a version control if we've got major changes to parts. Um, Over here, like we've got a lot of companies have some sort of like approval process or review process for drawings. So an engineer will create a drawing and that drawing will get handed to their boss and then the boss will check it and sign off on it. And this is basically just fields for people to put their initials in and whatever. There's fields here for material and finish. So, you know, we could put, you know, aluminum, and we actually know that it's 5052, so we'll put in the alloy as well. You know, if we're cutting it out of sheet, that's a common sheet material. And we could also put in the finish here. You know, we might just put deburr, or if it's getting painted, we could put paint black or whatever, right? There's also some other information in here for up here would normally be like a company logo. So like we could put the RoboChargers logo up here or something if we wanted to. You can put the weight. You can also create multiple sheets if you need more sheets to, you know, fully show all of the part geometry. You can create additional sheets, and this will show how many, you know, what sheet you're on. So that's kind of title. That's kind of a quick overview of the title block. I don't really want to go into too much detail beyond what I've just said because of basically we don't actually use this that much on the RoboChargers, and we won't be creating that many drawings in a season usually. So one other thing that I want to talk about here though real quick is what are called sheet tolerances. So basically every dimension on a drawing can have a tolerance. So the tolerance basically tells the manufacturer or whoever's manufacturing the part, you know, what, you know, I can make this at 2.740 inches, but I can't actually hit that number exactly. Like it might be 2.7401, right? Or it might be 2.7, you know, 399 or something. Like it might be very, very close. And if I round off the dimension, it'll be 2.740, but it won't be exact. And so obviously there is no such thing as an exact dimension. And so all of these numbers on the drawing are basically kind of giving a target that the manufacturer is trying to hit. However, they won't hit it exactly. And so what you as the designer need to do is specify what is the acceptable range for a dimension to fall in for the part to be considered good. So one thing that's probably easy to think about is the material thickness. So in reality, what's going to happen is you're going to go to you know, a material rack. You're going to buy. You're going to have, you know, some material that you have purchased that has some nominal size. You're going to pull that sheet off of the stack and you're going to make this part. You can't actually control this thickness exactly, so there has to be some range that's acceptable. And so, you know, if we double click on this drawing note, we can actually specify a tolerance scheme to show, you know, what's an acceptable limit. There's a few different common ways of doing this. So symmetrical is probably the simplest one, and this is basically just a plus or minus that says maybe I can go up 0.01 right on the material or something. So this is saying it needs to be 0.080 inches plus or minus, you know, 0.01 inches. So this could be as high as 0.09 or as low as 0.07, and it would be acceptable. So that one's pretty common. I can also, that's symmetrical. I can also do deviation, where the positive and the negative are different, and I specify them separately. That is also a very common way of doing it. This is more common for things like bearing holes and stuff like that, where, you know, you don't, you know, you might want it to be like, we don't want the sheet to be oversized or something. So we can go 0.000 for plus, but we're okay with it being undersized. We go 0.2, right? So now this can be 0.06, 0.06 to 0.08, right? It's plus 0 minus 0.02. Basically, this is also specifying the range. Now, from a manufacturing standpoint, there's also limits. Limits basically just to define the upper limit and the lower limit for the dimension. I find these a little bit easier to understand in certain scenarios. We'll talk about this kind of a little bit more here in a second, but this basically you are still specifying deviation here in this little box. However, it just displays the full number. It just kind of adds to whatever the base number is. We're going to just do deviation here. Oops, sorry, symmetrical. Do 0.01. That's fine. Okay, so then let's go back to our title block here. So essentially, each dimension here on the drawing, if I don't specify a tolerance like this, what you're supposed to do as a person reading the drawing is you're supposed to look at the title block, look at the number of digits of precision on each of the numbers of the dimensions and compare them to this chart. So basically, you would need to fill in, if we made a template here, you would need to fill in, what these tolerances are. Now, the idea is that these sheet tolerances are usually common across an organization. So a lot of companies will have a template. They will specify their sheet tolerances, and the sheet tolerances will be the same on every drawing. And that just makes it easier for the manufacturer. If the manufacturer gets used to, they memorize, or they have a cheat sheet or something where they know what the sheet tolerances are. They don't have to like constantly be looking at this title block. However, you can have different drawings for different purposes that have different sheet tolerances depending on what you're making. You'll notice this little location here also specifies the dimensions are in inches. That's important. They also specify fractions for tolerances for fractional dimensions and angular dimensions. So let's just fill in some numbers here. So generally the idea is the higher the tolerance, the higher the number of digits of precision, the tighter the tolerance. So like for 4 digits of precision, let's go 0.0005 inches. That's really tight. Like half a thou is really tight. 0.003, we'll do plus or minus 3 thou, plus or minus 3 thou, or 5 plus or minus 5 thou, somewhere in that range. This is pretty common for a 3-digit precision on an inch drawing. You'll see these vary. And then, 2 digits of precision, we'll say this is, plus or minus 0.01, I believe, is a little more common. These will not vary a ton from company to company, but they aren't exactly the same usually. And companies kind of figure out what their standard tolerances are so that if there's something that's super standard, they don't have to specify it, right? So the idea is that like with these dimensions here, these are all 3 digits. It's pretty easy to hit, plus or minus 3 thou for a whole position on a mill. That is, you have to be careful if you want to hit that, but you can hit it. Now, generally, I would say that sheet tolerances are supposed to be a little bit more on the loose side, and then if you have tighter tolerances, you specify a tolerance like this. Generally speaking, people that are reading drawings will kind of just assume that tolerances like this are a little bit tighter and more important than the sheet tolerances. If you had some dimension like, maybe this guy here, like we really don't care what this radius is. This is only here to like specify, we just don't want a sharp corner there. And so this radius being 3 digits of precision is pretty silly, right? We're not going to hit this within 3 thou. It's not important. So typically what we would do is we would reduce the number of digits of precision by going into this dialog box and changing this to like, 2 digits or something. But, maybe 2 digits is, 0.0110, it's plus or minus 10 thou. Maybe that's still too tight for what we're doing. And so, we could specify, a deviation of like, 20 thou instead, right? We could specify a bigger range, but that's typically a little bit weird to do. It's totally valid. It's just a little bit weird to specify a range that's bigger than your sheet tolerance. Generally speaking, when you're building a template or something, you want your sheet tolerances to be pretty loose, and then you specify tolerances that are more precise in the specific situations where you want. In terms of specifying tolerances in the context of FRC, it just does not matter. We are not going to check tolerances specifically during the season. What we will do is we will test fit the part on the robot, and if the part fits correctly and performs the function it's supposed to fit, then it's a good part. If the part does not fit, then it will need to get adjusted or remade. And so generally speaking, the tolerances in FRC are so loose that the machine that's making the part, whether it's the mill or the lathe or the router or the 3D printer, those are all more precise than the tolerances that we would need to set. And so generally speaking, it would be extremely rare for the router to cut apart, so far out of, so far away from the CAD model that we would need to, remake the part or something. The one exception to that is like when we're cutting parts that have bearing holes in them. A lot of you that were on the team last year will remember a process that we would do pretty frequently if we had like bearing holes in a part, whether it was polycarb or aluminum on the router. We would stop the router and we'd have it do the holes for the bearings, and then we would basically move the head out of the way, test fit the bearings into the holes on the sheet, and then if they were not quite right, we would go in and adjust the program and rerun the profiles, and it would recut the holes. And we were basically checking the tolerance of that hole by using the bearing to test fit the hole. So generally speaking, if you guys building the drawings here, building drawings like this for the RoboChargers this season, really specifying these tolerances is not something you need to do. They will get ignored, I can tell you right now, because we don't really have the time or the ability to kind of check these tolerances. And you might not necessarily know what the correct tolerance to put is. Basically, we're going to check things based more on fit and function rather than dimension. And so the only reason that I'm talking about these tolerances and sheet tolerances and stuff here in this kind of CAD video is that this will become much more important to you later in life as you become engineers and get your degrees and work for different companies, or go into manufacturing jobs and you guys are running machines and you're making things to spec. Like whatever you've got to do, like if you're working in the manufacturing and engineering spaces, this type of tolerancing will become important to you. So this is kind of just a quick primer, I guess. Okay, so let's talk about one more thing before we go here. I know this video is getting kind of long and kind of talky, and there's not a lot going on here. But I did want to talk a little bit about how you, like, where do you put these dimensions on the drawing? So basically, we decided that we were going to use this corner as a reference, and basically we were going to specify all the ordinate dimensions based on this corner. But why couldn't I just dimension this hole from the edge and then dimension the distances between all these holes? Like, why do I need to do an ordinate dimension? So this basically brings up kind of the concept of what I would like to call a manufacturing drawing versus an inspection drawing. Those terms are they're not super standard. I don't think that's necessarily a term or a name that everyone in the industry will use. However, the concepts are still pretty well established. So basically, the idea is what we have created here is what I would call a manufacturing drawing. So the primary purpose of this drawing is to make it easy for someone making this part to basically go up to a machine, hang this drawing on the machine, and drill holes on a mill or whatever, and make this part correctly. This drawing is based around making the job of the machinist easy. However, that is not the only purpose that a drawing can serve. And so in some cases where, maybe you're a company and you're sending a drawing to another company and another company is going to make the part, you are more concerned in that case usually with making sure that the part is made correctly, because you can't walk out to the shop and talk to the guy making the part and make sure they understand, like, okay, this whole position is really important, but this whole position is not, or this radius is not very important. But it's more important to specify what's important about the part and what the actual tolerances are, rather than making it easy for the person to manufacture from a readability standpoint, right? Having all of these holes referenced off of this side is super easy to use on a mill, because you can have you're going to drill these holes based on coordinates, and so specifying the coordinates on the drawing is super nice and handy. And so before we go any further, I want to just say, if you are making drawings for the RoboChargers this season, this is how you'll do it. You will make manufacturing drawings, because all we are concerned about is making the job of the person on the mill very easy, right? You'll hand this drawing to another student and they'll go make the part. You don't want to make them calculate the positions of all these holes because you put the dimensions on the drawing in a weird way. So basically, just to be very, very clear, for the RoboChargers during the FRC and FTC seasons, you will do any drawings you do will be manufacturing drawings. They will not be inspection drawings. So I'm going to show you what an inspection drawing would look like. It's just a slightly different way of arranging the dimensions. However, I just want to make sure that you guys understand that the inspection drawing is more of something you would use later in your careers, and it's not super important for the RoboCharger. So what I'm going to do here, I think I can just duplicate this. I'm just going to make a copy of this drawing, and I'm going to basically delete a bunch of dimensions and show how we might want to go about making what I would call an inspection drawing for this. So I'm going to delete these. I'm going to delete this. Okay, the whole callout can stay, the radius callout can stay, the thickness callout can stay, this overall distance can stay. So what I want to do now, so when I think about the actual function of this part, this outer surface, like out here, like this doesn't actually matter, right? Because if what's going to matter is the relationship between this hole pattern here and this hole up here. And so because this part is just going to bolt or rivet onto the holes on the tube that this mounts to. And if these holes are off, it moves the whole part. And so what's important is just that the relationship between these holes and this hole is controlled. And so what we're going to do here is I'm going to pick the dimension tool. I'm just going to dimension what I care about. And what I care about is that, this line of holes, and notice I picked the back hole here so that this dimension line extends through all the holes. That this line of holes is a certain distance away from this hole here. And then in addition, I care about, these two holes being in line. And then I care about maybe I care about the spacing of these holes rather than the relationship of each hole to the corner of the part, right? So maybe what I care about is, from here to here, right? Like maybe that's what I care about. And what we can actually do here is we can use a little trick so that we don't have to dimension each one of these individually. I'm going to drag this out to the side and then double click on it. We could put a little note at the back that's TYP and then dot, because it's an abbreviation. Then hit escape. Oops, I should put a space in front of this. Escape. This basically this is a little abbreviation that stands for typical, and it basically just means that anywhere this dimension is relevant, you can assume that this dimension kind of applies to multiple places. This is a dangerous thing to use on a very complicated part because it can become confusing very quickly which dimensions apply to which places. And that's why typical is a little bit of an older drawing standard that doesn't get used quite as much anymore. However, it's still totally valid. On a part like this is a perfect application for it because you know, it's very obvious that this is a very regular hole spacing. And so anybody looking at this drawing will go, 0.5 typical, meaning, oh, it's half an inch between each hole, right? And they'll just understand that that's implied. So now the thing to understand about from a tolerancing perspective about doing a drawing this way, I am dimensioning it this way because maybe I care about the hole spacing and I don't necessarily care about the position of this end hole relative to the first hole. But the thing to understand is that when I chain dimensions like this, like when I say this hole and this hole can be a half an inch apart, and then this hole and this hole can be a half inch apart, and then this hole and this hole can be a half inch apart, etc. down the line, that can become a very dangerous thing because what that does is if this dimension here has a tolerance associated with it. If we look at our sheet tolerances, it's 3 digits plus or minus 0.003 of an inch. And so basically, if we go, if these two holes get manufactured, on the edge of the tolerance, like they're 0.503 apart, right, which is the farthest they could be without violating the tolerance. So these two holes could be 0.503 apart, but these holes here could also be 0.503. So the 503 here, 503 here, 503 here. That's all within tolerance. But basically what that means, I've got 4 gaps that are each 3 thou over. That means that this hole is actually 12 thousandths of an inch farther away from this hole than it would be if all the dimensions were spot on, like all the spacings were spot on 500. So that's something to keep in mind, and that's what's called tolerance stack up, which is when I've got parts that have I have dimensions or components that have individual tolerances, and then those tolerances are chained in a line. Basically, if all of the tolerances end up towards the high side where they're like a little bit oversized, or if they all end up on the low side, I can have these big swings in dimension at the end. And that's a really big problem. That's, a very big part of engineering is at managing that tolerance stack up. And, sometimes the solution is just to apply a tighter tolerance. But however, the thing to understand is that whenever you apply a tighter tolerance, the manufacturing gets more expensive because it gets more difficult to hold that tolerance. So I don't really want to go into it any more than that because it starts getting a little bit advanced for what we're talking about here. But just be wary when you're specifying spacings like this that are part of a long chain. So then moving on a little bit here, let's just do some more dimensions. So now maybe I care about the location of this hole off the corner, but maybe I don't care about it that much. So I'm just going to do 2 digits for this because a looser tolerance. Let's do a dimension from here to there, kind of the same deal. I'm going to line these arrows up just to make it look nice. And I'm going to do 2 digits here as well because I don't care as much. Center this, look nice. And so I won't go any farther than this, but basically this drawing essentially conveys the same information that this drawing over here does. However, they're done in very different ways, and this drawing here is optimized for ease of use of the manufacturer, where this drawing here is optimized for basically conveying the design intent of the part and conveying what is important about the geometry of the part rather than making it easy for the manufacturer. Because, for instance, if you were on a mill and you needed to know what the coordinate of this hole was, you would have to add this dimension and this dimension together, and then you would have to like calculate out, 0.5 here plus 0.5 plus 0.5 to get the coordinates of these holes out at the end. And so both of these are valid. It's just very important to understand, when an inspection drawing is required and when a manufacturing drawing is required, and place your dimensions accordingly. So that's essentially as far as I want to go there. I think this illustrates the point relatively clearly. Like I said, though, focus on manufacturing drawings. Try to understand the manufacturing process as you're making the drawing, so that you can put dimensions in places that are useful. And you know, as the new students on the team and everything get kind of acclimated to this, all of the mentors are there to help you. You know, all of us have quite a bit of experience, you know, with the manufacturing processes and reading drawings and things. And so, you know, if you have questions about, you know, where you should put a dimension on a drawing and what's more readable, there's a lot of people on the team that can help you out and you know, and answer any questions that you have. So the good news is we're all kind of working in the same room during the build season. So if there's a drawing that gets printed out that's not super readable, the person making the part, it's very easy for them to come talk to you or, you know, a mentor or whatever, and we can change the drawing very easily and reprint it to make it more usable. And so there's kind of an iterative process to making these as well. And as you make more and more, you'll get used to, you know, how to get better and better at them. So it's you know, there's some repetition required to get good at this. So basically that's all we've got. Feel free to play around with drawings. You know, make drawings of more parts if you want. You know, and if you have any questions, you can ask me, and you know, I can review your drawings if you want some feedback on them. You know, whatever works best. So I will see you guys next week, and have a good one.